Intermediate Value Theorem. The intermediate value theorem is a very logical result that we discuss in AP Calculus, and I really feel like a lot of students already have this innate developed intuition about what it says. But when we start to get into the formality of it, everything gets lost and confused. So before we even look at the formal definition, I want to just talk about what you might already think of an example that we see every day that involves the intermediate value theorem. So when you first turn on your car and look at the speedometer, it reads what? Hopefully it should read 0. It should read 0 miles per hour, right? If you just turn on your car, it should be going 0 miles per hour. And now let's say when you're on the road, you glance at your speedometer, and now it reads 45 miles per hour. So my question to you is that at some point on your trip, can you guarantee that you were going exactly 25 miles per hour? So hopefully you've thought about it and you've decided yes or no. The answer is yes. The answer is absolutely yes. I can guarantee that you were going exactly 25 miles per hour if at some point you reached 45 miles per hour. In fact, I can guarantee that at some point you were going 1, 2, 3, 4, 4.5, 5. You get my drift. If you were starting at 0 miles per hour and you at some point reached 45 miles per hour, you had to somehow reach that value by crossing every single speed from 0 to 45. So that is a very informal way of introducing the concept of the intermediate value theorem. There was no way that you could skip 25 miles per hour if at some point you reached 45 miles per hour. So let's try to formalize this idea and look at a corresponding graph. The intermediate value theorem, or IVT, is a fundamental result which tells us that a continuous function cannot skip value. So in the previous example, it should be noted that speed is a continuous function, and that's why we couldn't skip going 25 miles an hour if at some point we were at 0 and we ended up at 45. There's no way we could skip 25 or really any number in between for that matter because speed is a continuous function. Now, the formal statement of the intermediate value theorem is one in which you will have to memorize word for word. So let's go through it piece by piece that corresponds to this graph here as well. If f of x is a continuous function on a closed interval from a to b. So here's my closed interval on the x-axis from a to b. So what that means is that we include the endpoints. So my continuous function is from f of a, and it's going to go all the way to f of b. So it's continuous on this closed interval. Then for every value m between f of a and f of b. So if this is the x value a, f of a is here on the y-axis, and f of b is also on the y-axis. So for every value m, so that means that m is a y value. So for any value m that I choose. So let's go ahead and say m is going to be this point right here. The final part of the theorem says that there exists, and I'll talk about why the word exist is bold and underlined in a second, but there exists at least one value c in the interval from a to b, and now this is an open interval, such that f of c equals m. So what is this saying? For any value m that I choose, so again, let's say I chose this m value between the two y values, f of a and f of b. There must have been some c value back between a and b, so not including a and b because it's an open interval. So in other words, there must have been something between a and b, some x value, that graphed you to the y value m, so such that f of c equals m. So for any value, any y value I choose between f of a and f of b, so let's say I pick this one here, there must be some value between a and b on the x-axis that corresponds to this particular number on the y-axis. So it looks like whoops, let's go ahead and try and trace it back. There we go. It goes back to, let's say, some C1. So let's call this M1. So there's some M1 that I chose between f of a and f of b, and there was some C1 that corresponded to M1. So that's the formal statement of the intermediate value theorem, that we cannot skip around is what it's informally saying. But formally, if I choose any y value, it better have come from some x value in the open interval from a to b. So the existence part. Let's go ahead and scroll down a little bit. The existence part. This theorem tells you that an x value exists, but it doesn't tell you what that particular x value is. So let's stop and think about that speed example for a second. So if you're going 0 miles per hour and then 10 minutes later you're going 45 miles per hour, the intermediate value theorem says that yes, at some time between 0 and 10 minutes then, you must have been going 25 miles per hour. But the intermediate value theorem doesn't tell you what time that happened. It just tells you that it happened. So it's what is called an existence theorem. It tells us that it definitely occurred, but can't really tell you very much more than that. But it's going to be a useful theorem for at least telling us that this happens at some point. And we're going to apply this theorem to a lot of word problems as we move further and further into the class. Alright, so this is sort of a special case of the intermediate value theorem. So it's its own theorem. It's the existence of zeros theorem, or important result. And here's what it says. It says if f of x is continuous on the closed interval from a to b. So again, so far, the same as the intermediate value theorem, continuous on a closed interval. So here we have our closed interval, and I am a continuous function all the way. And if f of a and f of b are non-zero and have opposite signs. Alright, so if f of a is positive and f of b is negative, or vice versa. So f of a and f of b, so let's look at our example here. So here, f of a, so here's a, f of a is a negative value, and f of b is up here above the x-axis, so this is a positive value. So we have a continuous function on a closed interval. But now we also need f of a and f of b to be not zero, and they have to have opposite signs. So one's positive and one's negative. In this case, f of a is negative and f of b is positive. Then what has to happen is f of x has to have a 0 in the interval from a to b, where a to b is now an open interval. So in other words, the function must necessarily, it has to cross the x-axis. So another, an equivalent term for a 0 on a graph is going to be an x-intercept, or a real 0 is an x-intercept. So this says that if one of the endpoints on the closed interval gave you a positive value, and the other one gave you a negative value, and remember that we're dealing with a continuous function here, so there has to be some place where I cross the x-axis. There has to be a 0. So if you can see on this graph, the 0 is marked right here, right? So there has to be at least one time when the function crosses the x-axis. Now there could be more than one, but there has to be at least one. So this too, and it's in the name, is an existence theorem. Right? It doesn't tell us what the 0 is, that the x-intercept is a particular number, just tells us that there is at least one place where we do cross the x-axis and that there is a 0. In this first example, we want to show that the function f of x equals x cubed minus x plus 1 has a 0 in the closed interval from -2 to 0. So here we have this cubic polynomial x cubed minus x plus 1. And hopefully we know the general shape of a cubic graph. So here is this specific graph. But we're assuming we don't know exactly what it looks like. But hopefully we know a general cubic is definitely going to cross the x-axis at some point. But specifically, we're trying to show that the function has an x-intercept, or a 0, between -2 and 0. So here we should be thinking the intermediate value theorem, and more importantly, that special case of the existence of zeros. So we have to start out by saying that f of x is continuous. So any polynomial is continuous everywhere. So we would have to write out, really everything that I've written here. So first we're going to note that f of x is continuous on -2 to 0, and we should even write because f of x is a polynomial. Alright, so the existence of zeros theorem says that what we need is that one of the endpoints, when substituted in, has to be positive, and the other endpoint has to be negative. That is what's going to guarantee that there's some place where we equal 0 or cross the x-axis. So what we're going to do is we're going to note that substituting -2 into the function, so -2 cubed minus -2 plus 1, well, that equals -5. So -5 is less than 0, so here we have our negative value. And substituting in 0, 0 cubed minus 0 plus 1, so into the original function gives us 1. That's greater than 0, so we have our positive value. So since f of -2 is negative, and f of 0 was 1, so it was positive, by the intermediate value theorem, there must exist some c, so some number, in the open interval from -2 to 0, such that f of c equals 0. Thus, f of x has a 0 between -2 and 0. So if f of x has a 0 in the open interval from -2 to 0, well, -2 to 0 closed, that's a bigger interval. So if there's some f of x between -2 and 0 on the inside of this open interval, well, there has to be one also in the closed interval. So we've used the intermediate value theorem to show that. So this is the corresponding graph, which definitely proves to you that somewhere between -2 and 0, this cubic polynomial crosses the x-axis or has a 0. So we can confirm that. So notice, at -2, I have -5 as my function value, and at 0, I had +1. So since 1 was negative and 1 was positive, there's no way I could skip the x-axis because I had to somehow jump from negative values to positive values, and that jump across the x-axis means that there was a 0. In this next example, we're going to use the IVT to show that f of x equals 2x cubed minus x plus 3 takes on the value 3.5 for some x in the interval from -1 to 1. So before we even start plugging in any numbers into anything, we have to guarantee continuity to use the IVT. So we have to state, we'll note that f of x is continuous everywhere because it's a polynomial. So I'm just abbreviating that, but we do have to somehow state it, otherwise we can't use the IVT. So now we want to show that the function takes on the value 3.5. So takes on meaning that for some x between -1 and 1, some value of x should be able to give us an output of 3.5. So when we substitute some number between -1 and 1 into this function, we should get out 3.5. Now, in this problem, we're not going to find that number, but we're just going to show that such a number exists because the IVT is an existence theorem. So the idea is that we don't know exactly what this function looks like, but we can go ahead and try to graph it to at least think about what this problem is asking of us. So I know that this has a y-intercept of 3. So at 3, I know this has a y-intercept, and I'm looking at only what's going on really between -1 and 1. And so this is a cubic function, so it might look something like, whoops, well, it has to go through 3. So let's go ahead and say maybe it looks something like this. Alright, so who knows exactly what it looks like? Something like this, some cubic polynomial has a y-intercept of 3. But we want to know is that it takes on the value 3.5. So where's 3.5? Let's go ahead and say it's about right here. That it takes on that value so that there's some function value that when we plug it in, we'll get out 3.5. So maybe I'll move this 1 over a little bit so that it does happen between -1 and 1. Or who knows, maybe it could happen over here somewhere. I just drew a rough sketch. So we want to show that this happens, that somehow this cubic function crosses the horizontal line where 3.5 would be. without actually graphing it or figuring out that number. So what we're going to do is we're going to take the endpoints that were given in the interval and we're going to plug them into the function. So let's go ahead and first take -1, plug it into f of x. So f of -1 is 2 times -1 cubed minus -1 plus 3. So here we'll get -2 plus 1 plus 3. So we get out positive 2. So we know that f of -1 equals 2. So already my graph is not really accurate, right? So at -1, what do I know? I go through the y value 2. So this is what I know, that points on the graph. I do know the y-intercept is 3. And now let's see what's going to happen at +1, the other endpoint. So f of 1 is going to be 2 times 1 cubed minus 1 plus 3. So we'll get 2 minus 1 plus 3. So 2 minus 1 is 1 plus 3 gives me 4. So when I substitute 1 in, I get out 4. So if this is a continuous function, let's go ahead and choose a different color here. If this is a continuous function, and I know that at -1 I'm at 2, and at 1 I'm up here at 4, and then I even have this extra knowledge that the y-intercept is 3, well then the function, maybe it looks something like this. But the idea is that if it's continuous, I should be able to draw it without lifting my pencil. So if I get out a value of 2 and I get out a value of 4, at the endpoints, at some point between -1 and 1, I had to equal 3.5, right? We don't care what this value is, just that it exists. So what we have to say is something like, since 3.5 is between, so I'm going ahead and using some mathematical notation here, since 3.5 is between, well, f of 1 and f of -1. So remember, f of -1 was 2, f of 1 was 4. 3.5 is between those two values. So 3.5 is my m. If you remember the actual statement of the IVT, for every m that I choose, there has to be some corresponding point between 2 and 4 that maps us or that takes us to the value of 3.5. So since 3.5 is between f of -1 and f of 1, there must be some c in the open interval from -1 to 1 so that f of c equals 3.5. So in formally using the intermediate value theorem, there is a little bit of writing involved. We have to state why we know the function's continuous. We have to show some algebraic manipulation to determine whether we get the right numbers for the endpoints to come out. And then we have to summarize how we use the intermediate value theorem. And I did, even though in the statement of the problem it says use the IVT, I should put by the intermediate value theorem, since blah blah blah. So I should include that I use the intermediate value theorem. Even though the problem told me to, in my result I should state that that's what I'm referencing here. Alright, let's take a look at some AP style questions that deal with the intermediate value theorem. So we're told the temperature F of T in Arizona was recorded every 30 minutes for a 3-hour period beginning at 7 a.m. So here's this table of data where T is in minutes after 7 a.m. So that means that 0 is exactly at 7 a.m. So we can say 0 corresponds with 7 a.m. And so every 30 minutes, the temperature was recorded. So F of T we can see is in degrees Fahrenheit. So at 7 a.m. or at time 0, because that's when we began recording information, the temperature was 64 degrees. And then 30 minutes later, so 7:30 a.m., the temperature had risen 6 degrees, so I'm at 70 degrees at 7:30 a.m. So now we can see that 180 minutes later, so 180 minutes, that's 3 hours later, so that means that this is at 10 a.m. By 10 a.m. in Arizona, it jumped up to 90 degrees. So one of the things I want you to note is that temperature is a continuous function. So we should be able to think about that the temperature can't just jump from 1 second to the next. We have to gradually increase. So temperature is considered a continuous function. So we need continuity to apply the intermediate value theorem. So the question itself doesn't tell us specifically to use the intermediate value theorem. We have to know to use it. So the question is asking us, is there a time t? So it's not prove there is there a time t between 7 a.m. when we start recording information and 10 a.m. when we finish recording information? Is there some time when the temperature in Arizona was exactly 80 degrees? Explain your answer. So here, we should be thinking the intermediate value theorem because the question is, well, is there a time when I'm exactly 80? So can I skip 80 degrees is the question. So if I look between 7 a.m. and 10 a.m., if I go from 64 degrees to 90 degrees, there's no way I can skip 80 degrees. So that's the informal conceptual understanding that I know my answer to this question is going to be yes, but my work has to be a lot more formal, and the way in which we write it has to be very technical and precise, down to the English language being a part of it, that it matters what order we put words in a sentence, and it's going to matter what order we put words in right now. So if we're using the IVT, to even begin using the IVT, we have to satisfy the hypothesis. So what I'm going to do is kind of categorize this as that I'm going to write, we have to satisfy the hypothesis to even use the intermediate value theorem. So you wouldn't actually write these two words down, satisfy hypothesis, but that's what we're about to make sure that we say that we did. So the hypothesis of the intermediate value theorem says that we need a continuous function. Well, the function's name is capital F of t. So capital F of t represents temperature, and temperature is continuous. So we talked about that makes sense, that we can't skip around. So that temperature is continuous. So what we want to say is note. So we want to say something like note, and there's no one precise way of saying it. I don't even want to see you copy exactly what I do every time and just fill in the blanks. It's understanding what's happening. So what we're doing here, however you are going to word it, we have to say, well, look, we can use the IVT because note f of t, we use the name of the function, f of t is continuous. So we write that down. Note f of t is continuous. So we've satisfied part of the hypothesis. The other part of the hypothesis says that the temperature that we're looking for, so in this case 80 degrees is between two other temperatures that are given. So we want to make this as clear as possible. When exactly does this happen? So it definitely happens sometime between 7 a.m. and 10 a.m. But we can narrow it down even further. So we can say that right here, actually, we know that the temperature at some point was 80 degrees right between here, because we can't go from 78 to 83 without at some point crossing 80 degrees. So let's think about that in terms of time, right? So this is going to be 8 a.m. So right here, this is going to be at 8:30 in the morning, it was 78 degrees, and then by 9 a.m. it was 83 degrees. So we know sometime between 8:30 and 9, it was exactly 80 degrees in Arizona. So we want to narrow it down even further. So to satisfy the hypotheses, we need the function is continuous, and we need to say, so I will continue in the same color, so f of t is continuous, and 80 degrees falls between, so what we need to do is say that 80 degrees is definitely between, and now here's the tricky part. We have to correctly use function notation. So 80 degrees, well, of course 80 degrees is between 78 degrees and 83 degrees, but I don't want to write such an obvious statement because it also doesn't reference the function. So notice we said f of t. So we don't want to write right now 78 degrees is less than 80 degrees, which is less than 83 degrees. That's like saying 1 is less than 2. Well, duh. We don't want to write something that general. We want to reference the function. So 78 degrees is f of 90. So right here, we're going to put f of 90. So it's like putting 78 degrees, but it's being specific and using function notation. So f of t is continuous, and f of 90, which is 78 degrees, is less than or equal to 80 degrees, which is less than or equal to 83 degrees, which we're going to represent as f of 120. So I'm going to go ahead and, in a different color, I'm going to just circle the part that actually would not be there. So this, this underline in 78 degrees and this underline in 83 degrees would not be there. So I just wrote that out so that you can understand where f of 90 and f of 120 were coming from. But this is the type of statement I need to write to show that I satisfy the hypotheses. So now, once you satisfy the hypotheses, the conclusion must be true. So the conclusion of the intermediate value theorem. So now, conclusion applies. So the conclusion, so if a function is continuous and there is some number trapped between two other values in given sets of information, then, so note f of t is continuous and this happens, then, so we will go ahead and change colors one more time. Then there exists, or there is, right? Then there exists a time t. Well, specifically, there's a time between 8:30 a.m. and 9 a.m. So there exists a time t in the interval from 90 to 120. So that's one way to say it. So between 90 and 120, or we could also rewrite this statement another way. We could say there exists some time t between 90 and 120. Or you could even say there exists a time t between 8:30 a.m. and 9 a.m. So I just want to make it clear that there's a lot of different ways to write this, and there exists a time t in this specific time interval. So yes, it definitely happens between 7 and 10, but we can be more specific. It happens between 8:30 a.m. and 9 a.m. So there exists a time t between 8:30 and 9 a.m. such that f of t, the function, the temperature, such that the temperature is 80 degrees Fahrenheit. So the part that we actually have to write is this. I actually have to write all of this out. So f of t is continuous and 80 is trapped between f of 90 and f of 120. Then there exists a time t between 90 minutes and 120 minutes, or between 90 and 120 in this notation, or between 8:30 and 9:30, such that f of t equals 80 degrees, and I am actually forgetting something extremely critical, by the intermediate value theorem, by the IVT. So I have to give credit where credit is due. This is a named theorem. It is very important, so I have to cite what theorem I'm using. In order to use or apply the theorem, I have to satisfy the hypothesis. That's this part in blue. Then the conclusion must apply. So this is a very advanced question. I mean, it is absolutely a part of an AP free response question, but you have to get used to being this technical about it and understanding how to apply an if-then statement. So you have to satisfy the if part, that's the hypotheses, and if you do satisfy all the components of the if part, then the then part, the conclusion, must apply, and we have to be able to write that form. Alright, let's try a second AP level question. So we have, let g of x be a continuous function. So we're just told straight out g of x is continuous on the closed interval from -2 to 3. What is the minimum amount of times that g of x must equal 0? Justify your answer. So now it's not, is it true that at some point g of x equals 0? It's, what is the minimum amount of times g of x has to equal 0, has to. So if I look at this table, I range in x values from -2 to 3, so I know I'm continuous across that span of all x values, and here are all my outputs. So what we should never do as means of a formal answer is draw a graph and just say, well, that's why. Just look at the graph. But we're going to look at the graph to gain an intuition. So we're just going to draw a quick sketch here of points. And we have -2, -1, so we're down here at -4, at -2. So we only know that this 1 point exists, -1, -2 is on the graph, 0, 1 is a point on the graph, 1, 3. So this was 1, we'll say 1, 3. 2, -1. So here's -1, so 2, -1, and then 3, -5. So way down here. So we definitely know that those points are on the graph. I'll turn them into a different color to make it more clear. Those points, and those points alone, that's all we know about this graph, and we know that this graph is continuous. But here's what I never ever want you to do for certain is connect the dots. Because at the end of the day, we have no idea what's happening between these points other than that they do connect in some way. But they don't necessarily connect in the way that everybody wants to connect them, which is just kind of in straight lines or really nice curves. So a lot of people just kind of want to do something like this. We'll connect these two and go up and then, turn down and go down again. So they want to say, oh, well, the graph has to look something like this. That is not necessarily true. This is one way the graph could look. And if this was the way the graph looked, how many times am I crossing the x-axis? Because if g of x equals 0, well, that means I'm basically being asked for x-intercepts. So how many x-intercepts are there? How many times do I cross the x-axis? So if the graph looked like this, then I cross the x-axis twice, right around here and maybe right around here. So 2 times is how many times I cross the x-axis. So what's the minimum amount of times? G of x equals 0. So it would appear to be twice, and that is in fact going to be the answer. And I didn't even have to graph it to be able to tell. What I had to look for was I had to look for places where g of x, the output value, changed signs. So between the x value -1 and the x value 0, the function g of x changed from negative to positive. So the only way to get from a negative to a positive is to cross the x-axis, is to go through 0. So I'm focusing in on these two sets of points right here, or on our graph that we sketched, it's, this x-intercept. And, well, I don't change signs between 1 and 3. I didn't change signs between -4 and -2. But between 3 and -1, I have to go through 0. So between the x values 1 and 2, g of x goes from a positive to a negative, which is right here. So that x-intercept here, which has to be to the left of 2. So this is another place where I have to cross the x-axis. So that's the minimum amount of times this has to occur, so twice. So why is it minimum? Well, because, like I said, we really couldn't graph this exactly and know what it looks like. So again, we never, ever, ever actually connect the dots. We do it just to gain an intuition about the answer if we need to. But truthfully, the graph could have looked like this. We could just go all kinds of crazy and go up and down, and then I could shoot down a couple times here and then go through this point again. We have no idea. Other than that I have to draw it without lifting up my pencil, we have no idea what it actually looks like. So it could have crossed the x-axis many more times than that, but by the IVT, it has to cross twice, wherever g of x changes from either negative to positive or positive to negative. But there were no sign changes between -4 and -2, 1 and 3, or -1 and -5. So I didn't have to change signs there. So that's just intuitively understanding it. Now we actually have to write it up. So now we have to say, well, we're using the IVT, so what do we need first is note g of x is continuous. So what we want to say is note g of x is continuous, and 0, so we're trying to show g of x equals 0, and 0 is between, well, 0 is between -2 and 1. So again, I don't want to actually write that. I don't want to put -2 is less than 0 is less than 1. So what I do want to write is using function notation. So instead of -2, well, that is g of -1. Whoops. So g of -1 is less than 0, is less than g of 0. So I'm using that function notation. So it's like saying -2 goes here and 1 goes here. But remember, we're not actually going to write that. We're just thinking it. So note g of x is continuous, and 0 is between g of negative 1 and g of 0, and 0 is also between g of 1 and g of 2, but I have to put the smaller value first. So remember, right here, negative 2 was less than 0, was less than 1. So in order from least to greatest, I have negative 2, 0, and 1. So right here, the values that 0 is between are negative 1 and 3. So I have to put g of 2 first. So notice g of 2, whoops, g of 2 is negative 1. So g of 2 is negative 1 here. Move things over a little bit. So g of 2 has to go first. And then g of 1 is 3. So g of 1 is 3. So this part is satisfying the hypothesis part. So we wouldn't need the bottom pieces. I'm going to erase those. Whoops. Nope, every time I try to erase that one, it does not want to go away, so maybe I'm not meant to erase that one. So now, I've satisfied the hypothesis. The conclusion would be, so by the IVT, there is at least 2 places x between the intervals negative 1 and 0 and 1 and 2 such that g of x equals 0. So let me go ahead and highlight which part is which. This part here is satisfying the hypothesis. And once I've satisfied the hypothesis, both that the function is continuous and 0 is trapped between, so the thing I wanted to show, g of x equals 0, that number is trapped between 2 other values of g, and 0 is trapped between 2 other values of g because we were trying to show it happens twice. Once I satisfy the hypothesis, then I can show that the theorem applies. So then there has to be at least, well, 1 at each time, so at least 2 places x. Once is between negative 1 and 0, and another is between 1 and 2, such that g of x equals 0. And the way we write this part, again, could vary too. So at least 2 places we could have written negative 1 is less than x is less than 0, and between 1 is less than x is less than 2. There's a lot of different ways that we could write it. I think what a lot of people struggle with is writing this piece right here correctly. So just one more time, why does it look like a 2 is first, right? Because this is one whole thing. G of 2, this is like a negative 1. So negative 1 is less than or equal to 0 is less than or equal to g of 1. So g of 1 is 3. So I have to go smallest to biggest. So I don't look at what the function's being evaluated at. I'm looking at what is the actual value of the function at this particular number. So I think it looks really tricky to a lot of students exactly which way the order goes, but the sooner you can get it straight in your head, the better, because this is not the first theorem that we're going to learn this year, or this is not the last theorem we're going to cover this year that has to deal with tables like this and understanding how to write this type of inequality.